Okay, let's unpack this. We're doing a deep dive today into a machine from the mid-1980s that made this one truly audacious claim.
Oh, yeah.
It claimed to be blindingly fast. And this isn't, your everyday home computer. It's not the beige box everyone remembers.
Not at all.
This is the TDI Pinnacle, a multi-user microcomputer that really tried to carve out a super specific niche based purely on raw speed.
And it was doing this in an era that was just, I mean, it was completely dominated by the growing and, let's be honest, often lumbering bulk of the IBM PC.
Right.
What's so fascinating here, I think, is just the sheer necessity of this machine's existence.
Yeah.
You have to understand the company, TDI Technical Development International.
They were Bristol-based, right, a British firm.
Bristol-based, yeah. But they weren't primarily manufacturers, which is key. They had built their whole reputation on being these expert importers and distributors.
So they were tastemakers, in a way.
You could say that. Yeah. Their bread and butter was the Sage range of Supermicros, which were machines already very highly regarded for their performance. And crucially, they also distributed the UCSD P system in the UK.
So they were already the go-to people for performance hardware and software. They knew what fast actually looked like in the British market at the time.
Exactly. So the Pinnacle machine itself, it wasn't even homegrown. It was actually the result of this cooperative agreement they had with an American hardware designer, Pinnacle Technology of Texas.
I see. So TDI basically took this very specialized American hardware,
Yep.
badged it as their own, and then just slotted it into their existing high-performance lineup.
They sold it right alongside the Sage range.
Yeah.
And this wasn't a product designed to, compete with the Commodore 64 or the Amiga. Their mission was surgical. This machine was aimed squarely at two markets where speed wasn't a luxury. It was a fundamental constraint on productivity.
Which were?
To the education sector, for one, and maybe most importantly, software development firms.
And when they launched it with that claim, blindingly fast, they weren't just using marketing fluff. The sources we have, they completely back this up.
Oh, they back it up in spades. It was absolutely quantifiable speed. Personal Computer World magazine, which was a really critical voice back then, put the Pinnacle through a whole series of rigorous bench tests.
Right.
The results were, well, they were unequivocal. The Pinnacle immediately seized the speed title. It easily became the fastest micro the magazine had ever tested.
That's incredible. And the previous champion.
The previous champion, ironically, was one of TDI's own imports, the Sage machine.
So they beat their own record. That's a seismic shift in performance for 1985. We should put this in perspective for you listening. This is a time when the world is watching the rise of the IBM PC, and on the higher end, you've got the revolutionary Apple Macintosh.
And both of those machines, the PC to some extent and definitely the Mac, used the Motorola MC68000 processor, the same core engine that's inside the Pinnacle.
But not in the same way.
Not even close. I mean, the core spec reveals the engineering difference. The other machines, they often ran the 68000 at, 8 millihertz? Maybe 10 if they were really pushing it.
Okay.
The TDI Pinnacle was running that chip flat out at a truly staggering 12 millihertz.
Yeah.
And the absolute game-changing ingredient that made that possible
Was the absence of wait states.
the absence of wait states.
Yeah.
Zero. None.
We are definitely going to spend some serious time on no wait states because that is the engineering flex of this entire machine. But before we get under the hood, let's just give some immediate perspective on what this level of performance actually costs.
Because it was not cheap.
No. Even the most specialized user has a budget.
And this was a colossal investment. The entry-level Pinnacle system in 1985, that's the one with just 256K of RAM and a 10-megabyte hard disk, that cost £4,995.
4,995 pounds. In 1985 money, if we bring that cost forward using modern inflation metrics, you're looking at the equivalent of roughly 19,900 pounds today.
For the base model.
For the base model, just the gray box itself.
Exactly. And that price point immediately disqualifies it from almost any kind of mass market competition. This was institutional, professional grade hardware. It was designed for a university lab or a software house with deep pockets where saving, say, 5 minutes on every single code compilation absolutely justified that 5-figure investment.
It's important to keep that sticker shock in mind as we look at the hardware because every single design choice they made was a trade-off between that cost and the ultimate speed. Okay, so moving from that eye-watering price to the actual physical machine, the TDI Pinnacle, you hit this immediate paradox. When I hear fastest micro ever tested, I'm picturing a huge rack-mounted server. or some kind of, hulking tower.
But it wasn't. It was surprisingly small.
It was tiny.
Remarkably compact, especially when you consider its power and its multi-user focus. It measured only 17 inches wide, 11.5 inches deep, and just 4 inches high.
So it's basically the size of a modern, a large pizza box.
Pretty much. And if you put that next to what the source calls the vastly oversized proportions of something like a standard IBM PC or some of the older, bulkier mini computers, the Pinnacle just looked like a desktop accessory.
Even though it was one of the most powerful microsystems available.
It's a real testament to the density of that 68,000 architecture and the custom engineering they poured into it.
Let's talk about the construction. The sources describe it as having an elegant and simple construction using sheet metal. That sounds a little utilitarian, maybe even cheap compared to the sleek, injection-molded plastics we were starting to see on machines like the Apricot.
Right, you'd think so, but it was a very conscious trade-off. It was one rooted in smart market economics, not cheapness.
Okay.
The source material explains that sheet metal was just a much better material for comparatively low volumes. The cost of tooling up for injection-molded casings is, well, it's astronomical. The source even joked that grown men have turned white at the cost of tooling up.
So for a niche machine like the Pinnacle, it just wasn't worth it.
Not at all. Sheet metal fabrication, using just two pieces, the bottom bent up for the front and back, the top bent up for the sides, is the pragmatic, reliable, and cost-effective way to go.
Function over factory glamour.
100%. This is a machine built by engineers for engineers.
And the front was certainly minimalist, just a simple, sticky plastic strip with the Pinnacle name and the TDI logo positioned above a single half-height floppy drive and a half-height hard drive.
The real identity of the machine, its whole purpose, is really defined by what's on the back, the I/O hub.
Right.
You've got the standard stuff, cooling fan on-off switch, power input, small reset switch. But the true mission statement of this machine is written in the connectors.
And that is?
7 RS-232 serial ports.
7. That is a massive commitment to multi-user capacity for a machine this small. For anyone listening, RS-232 was basically the standard way you connected a terminal or a modem back then. It was kind of the precursor to USB. But serial, much slower and much more demanding on the main processor.
So managing 7 of those simultaneously requires some serious internal orchestration.
The density of those ports just speaks volumes.
It really does. And next to them, you also had one decidedly unstandard Centronics parallel printer port. And then you hit the final, almost antique-looking feature.
The DIP switches.
2 banks of them embedded right into the back panel.
These are the tiny little banks of sliding plastic toggles. Why on earth were those on the outside of the machine?
They were a direct hangover from the older Sage micros that TDI distributed, and they were absolutely essential for low-level configuration.
So what did they control?
Critical settings. Things like communications line parameters for all those serial ports, hard disk partition boot selection, and other system settings. And the reviewer praised this design choice, noting that having them externally was so much better than the common practice of burying them deep inside the casing.
Which would require a full disassembly just to change a baud rate.
Exactly. This was a massive quality of life improvement for the system administrator who had to manage all 7 of those serial lines.
Okay, so let's talk storage and the noise factor. The review machine had a 21 megabyte hard disk, which was a very healthy capacity at the time.
It was. The configuration options went from 10, 20, or 32 megabyte hard disks. The performance was noted as being excellent. The disk worked well, but, and this is the classic 1980s caveat, it was very noisy.
The sound of progress. You could always tell where the powerful machine was in the office by that constant churning and whirring.
It really sounds like the physical box, while small, was constructed purely to house these powerful industrial components that prioritize performance and reliability way over office tranquility.
Yeah.
Right. Now we get to the core of it. The engine room, the TDI Pinnacle, and specifically the technical secrets that made that speed claim verifiable and worth that, 19,900-pound price tag.
Okay, this is where it gets really interesting. We know the main board was dominated by the Motorola MC68000, but the way they used it is the stuff of legend. Tell us again why 12 megahertz, specifically with no wait states, was such a monumental achievement in 1985.
Okay, so you have to understand the concept of a wait state. Imagine the processor, the CPU, is a speed reader. It's capable of devouring words at 12 million cycles per second, 12 millihertz.
Right.
The memory, the RAM, is the bookshelf. If the bookshelf can only deliver the next page of data at, say, 8 millihertz, the speed reader has to stop. It has to pause and wait for the new page to arrive.
And that pause is a wait state.
That pause is a wait state. It's just wasted processor time, and it absolutely kills performance.
So if they're running the CPU at 12 millihertz, they need memory chips and, crucially, a circuit board that's capable of delivering data to that CPU at the full 12 millihertz speed. No signal degradation, no timing errors.
Precisely. To run the 68,000 at 12 millihertz with zero wait states means that every single instruction cycle is used for actual work. This is the ultimate benchmark for system efficiency. It demands extremely high standards in your component quality, your timing control, and most critically, your circuit board fabrication techniques.
To ensure perfect signal integrity.
Perfect signal integrity, and this is where the U.S. defense connection comes into play, isn't it?
It is. This wasn't just standard PCB manufacturing.
That's right. The source material connects the dots directly. TDI's American partner, Pinnacle Systems, specialized in making circuit boards for the U.S. Defense Department.
So they were using military-grade fabrication processes.
Exactly. Think higher quality copper traces, multi-layer boards with strict impedance control, highly reliable component soldering techniques that are usually reserved for, like, avionics or mission-critical systems.
And this ensured the electrical signals were so clean and the timing was so precise
That the 12 megahertz clock could just operate flat out without ever having to slow down and wait for data to catch up.
But this must have exponentially increased the cost of the main board. I mean, was that level of specialized defense-grade fabrication really worth the trade-off?
It absolutely was, because the target market was willing to pay for time saved. For a software developer, if you cut your compilation time by 50%, that means getting your product to market weeks or even months faster.
And the money saved there.
Dwarfs the initial hardware cost. Plus, that military-grade reliability translated directly into rock-solid performance for a multi-user system that just could not afford random crashes when you've got 7 people connected and working.
Okay, let's look at the memory architecture that was supporting all this speed. The main board could hold 512K of RAM. The review system had a full megabyte, which was immense for the time.
And the additional 512K was housed on an expansion board piggybacked directly underneath the main RAM area.
Piggyback.
Yeah. Now, the reviewer did note that this arrangement left very little space for air circulation over that piggyback board, which could be a thermal flag.
A little worrying.
A little bit, but they confirmed that in practice, the machine ran fine. It didn't have overheating issues, which again just speaks to the robust component choice.
And the physical construction of that RAM is this beautiful piece of 1980s history. It sounds less like a computer and more like a work of art dedicated to redundancy.
It was an incredible sight. You had 144 individual 64K by 1 chips, all meticulously arranged in 128K rows of 18 chips.
18 chips, not 16.
18. And that specific arrangement was key because it provided parity checking on every single byte.
Which is crucial for systems that need high data integrity, especially in a multi-user environment.
It's non-negotiable for institutional clients. If a single bit flips because of some electrical noise or a random error, the system knows instantly.
That's reliability engineering right there. And the future potential was even bigger. The sources note that once the next generation of 256K RAM chips became available,
the Pinnacle's capacity would leak to a staggering 6 megabytes.
6 megabytes of RAM in the mid-'80s was basically mainframe territory.
It was. It shows the architecture was designed for massive scalability, ready to handle even heavier multi-user loads and much more complex software. You also had these little details that added to the robustness. 8K of ROM held the bootstrap and diagnostics. And a dedicated rechargeable battery kept the real-time clock calendar chip powered up.
So your records and logs were always accurately timestamped.
Always.
So we have this screaming fast CPU and this incredibly reliable parity-checked memory. But remember, this box had 7 serial ports all demanding attention. How did they handle the I/O bottleneck?
Well, you can't have your main CPU doing all that grunt work. You need dedicated I/O processing chips.
So they offloaded it?
They offloaded it. They used 4 Zilog Z80 DART asynchronous communication controller chips to drive those 7 RS-232 ports.
The Z80 family, a classic.
A very popular, well-understood processor family, known for its efficiency in handling peripherals. By deploying 4 of these controllers, They took that massive repetitive task of managing simultaneous incoming and outgoing serial data completely off the main 68,000 processor's plate.
It's a distributed processing approach. You let the Zilog chips handle the slow communication handshake so the 68,000 can just focus on crunching data at 12 megahertz.
Yeah, and the default baud rate was 19,200, which was quite fast for a terminal connection back then, and it was all configurable either through software or those external DIP switches.
And that brings us to the last major speed secret, the floppy disk drive. This one sounds like pure genius, but also potentially proprietary. How did they get very fast access times on a simple floppy drive?
This is a masterclass in aggressive optimization. Most floppy drives of that era had to use something called interleave or skew factors when they were writing data.
Right, so they'd write block 1, then skip a few sectors, write block 2, skip a few more, and so on.
And they did that because the physical speed of the disk spinning was just too fast for the slow processing speed of the CPU. By the time the computer was ready to tell the drive to read or write block 2 had already physically spun past the read-write head.
And you'd have to wait for almost a full revolution to access it again. Wasted time.
Much wasted time.
Yeah.
The Pinnacle bypassed this delay entirely.
How?
Because the 12 megahertz CPU with 0 wait states was so incredibly fast, it could process the data from the first block almost instantly.
So it was always ready for the next part.
It was always ready. Therefore, the system laid consecutive blocks of data end-to-end over the disk surface. No gaps.
That is a phenomenal insight. They leveraged the CPU's excess speed to completely eliminate the mechanical penalty of disk access.
It saved all the time that was usually lost waiting for the next block to rotate back into position. It meant the disk, while still being really noisy, performed like a far more expensive high-speed device.
The trade-off, of course, is that any disk written with this method was almost certainly unreadable by a standard IBM PC or a Mac.
Absolutely.
Cool.
Which just reinforces the system's specialized, closed ecosystem.
Okay, moving on to section 4. The speed of the hardware is one thing, but it only matters if the operating system and the user ecosystem can actually use it effectively, especially across 7 different users.
Absolutely. So you have this powerhouse sitting on the desk. Now you need peripherals. Since it used standard RS-232 ports, the system could technically work with, virtually any remote terminal.
It even came with a basic, plain vanilla terminal driver.
It did, but the documentation was very clear. That driver was notoriously slow. It was really only meant for basic compatibility. They expected you to load a faster custom driver as quickly as possible.
And TDI's recommended terminal was the American Wise 50, which they often just rebranded with TDI stick-on badges.
Yeah, and that was a conscious push toward modern ergonomics. The reviewer praised the Wise 50 because it moved away from the, and I quote, bulky, ugly DEC VT100 style terminals that were just everywhere at the time.
So the Wise was more modern looking.
Much more. It was low profile, the screen was large, it had full tilt and swivel capabilities. It even had a little thumb wheel for brightness control. It was designed to look sleek and professional in a corporate or an academic setting.
And the input device, the keyboard, was clearly built for serious, heavy work.
And the keyboard was key. It was a 101 key beast with 16 function keys running across the top. The feel was described as fairly springy with good tactile feedback.
And I love this detail from the review.
Oh, me too. The reviewer noted that the F, J, and the numeric 5 key had these small physical lumps molded right onto the keytops to help with touch typing.
That level of attention to user detail aimed at maximizing typing speed just shows this was a machine built for continuous data entry and coding.
The only criticism, apparently, was that the return key was oddly small.
A small return key aside, the ecosystem was ready. Now for the brain of the operation. The operating system. The standard OS was the UCSD P system.
It was, but they also offered CPM68K and something called MBOS, which was the multi-user business operating system.
And the choice was dictated by the market you were in.
Completely. Business users, like accountants or small firms, they would almost always take MBOS, or BOS as it was known, because it had this really established library of high-quality multi-user business software ready to go.
But the entire philosophy of the Pinnacle, its speed, its flexibility,
that was best utilized by the UCSD P system. That was the definitive choice for educational establishments and for software developers.
Okay, let's get into the P system. It has this reputation for being powerful, but also maybe a bit overly academic. Why was it so perfectly suited to the Pinnacle's architecture?
Because the P system was designed from the ground up to be portable and efficient, using an intermediate P code that was compiled on the fly. And crucially, it was engineered to exploit massive amounts of RAM, which the Pinnacle provided.
And this leads to its greatest system optimization trick.
It does. Here it is. One of the P system's first acts after booting up was to copy essential system files into the different users' RAM disks.
Ah, the RAM disk. So this links back to that noisy but fast hard disk. They essentially eliminate the storage bottleneck by moving the operating system files into that gigantically fast memory.
Exactly. Each user gets their own temporary lightning-fast workspace that resides entirely in RAM. The system file access speed goes from milliseconds down to nanoseconds.
Now that must require a fair amount of RAM for each user.
It does, which is why the Pinnacle's large memory capacity was so essential. But the resulting speed boost made an already fast system even faster. The system administrators could allocate the size of this RAM disk through the setup utility.
So if I'm a programmer and I'm constantly calling compiler files, I'm pulling them from RAM, not from that noisy mechanical disk.
Precisely. Like keeping all your tools right there on your desk instead of having to walk to the storage shed every 30 seconds. It is pure workflow acceleration.
And despite its academic origins, the P-system interface was apparently manageable, even for, a cynical CP/M or DOS user.
The reviewer, who admitted to being skeptical at first, found it surprisingly structured. It offered 12 self-descriptive top-level commands right there on the screen.
Things like
EDIT, RUN, FILLE for file management, CUMPILE, LINC, and ASEM for assembly. You didn't need to memorize a vast array of keywords. The options for what you wanted to do are presented really clearly.
the FILer function, the file management utility, that sounds particularly complex. It offered 20 menu options.
Yeah, the FILer was a full-service system management tool. It offered basic functions like SAV, remove, and transfer, but it went way beyond that. It managed the complex structure of logical and physical volumes, how the P system organized disks and data devices.
And among its 20 menu options was the infamous kernch command.
Kernch, which the original source just sort of guessed meant file crunching.
But it was more specific than that.
Oh, yeah. In the context of the UCSD P system, kernch was typically used to optimize disk space. When you delete or move files, they often leave unused sectors scattered all over the disk.
So kernch would reorganize the disk volume?
To consolidate all the free space into one contiguous block, which was essential for maintaining high performance and clean disk utilization. It was basically the early 1980s version of a disk defragmenter, all built right into the operating system menu.
Okay, so finally, the core mechanism for multi-user operation time slicing. How does the P system manage 7 people at the same time without slowing the whole experience down to a crawl?
So time slicing is the mechanism where the operating system takes that 12 millihertz processing time and it just divides it into tiny, tiny slices. It allocates each user a fraction of a second in rotation. So in rapid succession, user 1 gets a slice, then user 2 gets a slice, and so on, all the way to user 7.
But if the CPU is only 12 millihertz, dividing that by 7 sounds like it should severely degrade the performance for each person.
And it does slow down the performance per user, but here's the essential point that the reviewer noted. Because the system was so blindingly fast to begin with, running at 12 millihertz with 0-8 states, even when you divide that incredible speed by 7, the performance per user will still look good by comparison with other micros running single-user systems.
It was confidence born of just absolute raw processing speed.
Exactly. It enabled seamless background operation foreground response, even with a full house.
We've covered the engineering flex, the specialized software, and the physical noise. Now we move into Section 5, the proof. Did the machine actually live up to the hype when you put it under stress? The benchmarks section is the definitive moment for the TDI Pinnacle.
This is where TDI justified that nearly 20,000 pounds price tag. The basic benchmarks were run, and the results, well, they just confirmed the machine's absolute superiority over its peers.
So how did it do against the previous champion, the Sage 2?
The Pinnacle wasn't just marginally faster, it was over twice as fast.
Twice as fast?
Over twice as fast. That margin puts it in an entirely different performance class.
But the truly revolutionary finding, the one that validated the whole multi-user concept and makes this machine a legend, was the stress test.
Oh, yeah.
They ran the basic benchmarks simultaneously for all 7 users, a synthetic, massively processor-bound job designed to bring the system to its knees.
And the result was just astonishing. It was utterly compelling. Even with all 7 users running these complex time-consuming calculations at the same time,
Yes.
the system, when measured against the baseline, was still faster than a single-user IBM PC running the same test.
Let me just underline that for you listening. This tiny 4-inch high box, dividing its attention and its processing power among 7 separate users, still outran the industry standard running in a dedicated single-user mode.
That statistic is the core argument for the Pinnacle's existence and for its success in that niche market.
It proves that all those engineering choices, the zero-weight state, the parity RAM, the distributed I/O, they were necessary and they were incredibly effective.
The speed boast wasn't just accurate, it was an understatement, especially when you view it against the competition.
And TDI loved using these capabilities in their demonstrations, didn't they? They often turned to the classic algorithmic challenge, the Towers of Hanoi puzzle.
Yes, the Towers of Hanoi is a perfect recursive problem to demonstrate raw computational efficiency. The Pinnacle solved the puzzle in a mere 39 seconds. It was a quick, dramatic way to show just how fast that 68,000 could chew through complex logic.
So the speed is proven, but running a high-performance multi-user system demands deep configuration control. And that's where the utilities, especially the complex UN figure, came into play.
Configuration was necessary, but it was often user hostile. The system came with low-level utilities like disk backup restore and the highly recommended hard drive head parking utility.
You had to park the heads before you turned it off.
Oh yes, but the core utility for tweaking every single parameter was called UN figure. It let administrators fine-tune the floppy drives, serial ports, users, the real-time clock, system buffers, disk partitions, everything.
The problem, however, was this classic 1980s gatekeeper challenge. The UN figure utility required serious technical knowledge.
It absolutely did. The reviewer noted that the main issue with most of the configuration screens was that they required a knowledge of hex.
Hexadecimal.
You weren't typing in simple decimal numbers for parameters. You were often dealing directly with memory addresses or complex system flags that were all represented in base 16 notation.
Imagine trying to set up your printer port and having to calculate the buffer size in hexadecimal. That would send most modern users running for the hills. It really highlights how demanding system administration was in that era.
It certainly reinforces that this was a machine sold to experts. But thankfully, TDI recognized that even an expert system admin might occasionally want a reprieve from base 16 math.
And so they created the special easy setup system.
The easy setup was the lifeline. It was the user-friendly interface where all the numbers were mercifully expressed in standard decimal.
And what were the most critical tasks users could perform there?
The easy setup focused on the most common performance bottlenecks, which was primarily allocating system resources. The first function was setting the size of the buffers for the 7 serial ports and the printer port.
Why is that allocation so critical to the performance of a multi-user system?
Because your peripherals, printers, terminals, are orders of magnitude slower than the CPU. If the processor sends data directly to a slow printer, the CPU has to actually pause and wait for the printer to accept the next chunk of data.
Tying up the precious 12 megahertz chip.
Exactly. But by allocating a buffer, a small chunk of fast RAM, the CPU just dumps the data into that buffer in a microsecond and is immediately freed up to go back to serving the other 6 users. The printer then slowly drains the buffer in the background. It prevents the entire system from bogging down because of one slow peripheral.
So the system admin had to decide the trade-off. A bigger buffer for a slow printer to maximize CPU efficiency, or using that RAM for other critical tasks.
And the system even showed you the limit of available RAM at the bottom of the screen to guide you in making those crucial decisions.
And the second key screen in Easy Setup.
That was dedicated to user resources. This is where you allocated the size of each user's RAM disk, that hyper-fast temporary workspace, and determined which serial port that user was connected to.
So you could tune the machine based on usage.
Precisely. If user 1 was a programmer compiling massive code, you might allocate them a 256K RAM disk. If user 7 was just doing basic text entry, maybe they only get 64K, and you save the rest of the memory for the system buffers. It was all about maximizing that 12 megahertz chip for the users who were generating the most high-value work. So we arrive now at the final analysis of the TDI Pinnacle, who actually bought this incredibly specialized system, and what does its market position tell us about technology adoption in the 1980s?
Let's just quickly review the cost one more time just to reinforce the scale of this investment. The top spec system with a megabyte of RAM and a 32 megabyte hard disk costs 6,995s in 1085.
Which translates to roughly 27,900 pounds in today's context.
And that's before you even buy the terminals.
Right. Each Wise 50 terminal was another 695 in 1985, which is about 2,750 pounds today.
So if you ran the machine for the full 7 users, the investment in terminals alone would be over 19,000 pounds in modern costs. This was not a volume play.
Not at all. TDI knew this was not a mass market machine competing with the ubiquitous IBMs and apricots of the world.
So who exactly was willing to fork over what could easily amount to 40,000 pounds or 50,000 pounds in modern money for this small gray sheet metal box?
Well, the first key market was education, specifically for demanding tasks like data logging, psychological research, and straight data processing in university environments.
Right.
When you're running an experiment and you're collecting large real-time data sets from multiple sensors or multiple users, you need guaranteed processing speed. And crucially, you need that parity-checked RAM for data integrity.
The speed meant less downtime and faster research cycles?
Absolutely. And the second, and arguably the most crucial market, was software development.
Of course.
Software developers loved the Pinnacle precisely because compilation is inherently a processor-bound task. They were working on complex projects, likely using the P system's efficient Pascal or other high-level languages.
And reducing the time spent waiting for code to compile, that loop of edit, compile, test, edit.
Translates directly into saving thousands of pounds in programmer salary time. If the Pinnacle saved a team just 1 hour a day, that quickly justified the 20,000 pounds initial investment.
So this confirms that the Pinnacle existed in this very specific, high-performance, cost-justified niche where speed was a direct economic multiplier. What was the ultimate verdict on this machine?
The machine's strengths were undeniable. High performance, incredible component reliability, and a remarkable lack of bulk, which made it highly functional in crowded labs and offices. The reviewer concluded that this was a very nice, fast, multi-user machine and confirmed that the blindingly fast boast was absolutely accurate, even when it was operating under maximum load.
So TDI was savvy. They targeted their sales where the mainstream competition just couldn't touch them on performance per pound spent.
They succeeded by doubling down on speed and reliability instead of trying to chase the features or graphical interfaces of the mass market.
So what do you take away from this fascinating dive into the TDI Pinnacle? This was a machine that really defied the trends of 1985, prioritizing this invisible efficiency over visible features.
The core insights, I think, lie entirely in the engineering trade-offs. First, the technical marvel of that 12 megahertz zero-weight state MC68000 processor. That was only achievable because they leveraged specialized military-grade circuit board fabrication techniques.
That was the unshakable foundation of its speed and reliability.
It was. And second, the clever systems optimizations they applied to all the supporting hardware and software. That floppy drive speed hack that eliminated interleave by just trusting the CPU's velocity, and the genius of the parity RAM layout ensuring data integrity for all 7 users.
And finally, the efficiency of the software ecosystem, driven by the robust UCSD P system.
Yeah, its design allowed it to bypass all those I/O bottlenecks by using the RAM disk optimization, making sure that the system's colossal processing power was maximized for crunching code or data, not for waiting on slow mechanical parts.
The TDI Pinnacle might have been a footnote in computing history, never achieving the fame of the Mac or the ubiquity of the PC, but it was a true hot rod of its generation.
Which raises a final, maybe provocative thought. The Pinnacle demonstrated that in the mid-1980s, when the public was standardizing on the desktop metaphor in the PC format, the real leaps in raw computational power and complexity were often happening in these high-cost, specialized, and frankly invisible systems. These niche machines, built for programmers and for researchers, were accelerating the speed of innovation dramatically. They were establishing performance benchmarks and engineering standards that would only trickle down to the mass consumer market years, or in some cases, even a decade later.
So the fastest computer in the world often looked like a simple gray box and only talked in hexadecimal. A fascinating deep dive into a machine truly ahead of its time.